While training a machine learning model, we have to accurately estimate its quality. Take a high-stakes scenario, analyzing mammograms to identify if a patient has breast cancer or not. The model faces two possible ground truth states. The patient either has breast cancer or does not. Based on the data, the model can make one of two binary predictions. This 2x2 grid represents the confusion matrix, mapping those predictions against the actual ground truth. When the algorithm makes a correct prediction, the outcomes fall into two categories. A true positive means the mammogram shows cancer, and the model identified it. A true negative means the image does not show cancer, and the algorithm correctly said so. Errors happen when the model guesses incorrectly. A false positive occurs when the algorithm claims to detect cancer, but there is none. A false negative means the disease is actually present, but the algorithm missed it. The naming rule is simple. True or false indicates if the model was right or wrong, and positive or negative is the guess the model made. The confusion matrix organizes all these raw outcomes in one place. But the matrix itself isn't a single score you can use to easily rank models against one another. It is strictly the baseline data required to calculate actual performance metrics. The most intuitive metric is accuracy, the ratio of correct predictions to total predictions. Look at this visual scale showing a dataset of 100 mammograms. 95 are negative, and only 5 show actual positive cases of cancer. If you have a completely broken algorithm that simply classifies every single sample as negative, it logs 0 true positives and 0 false positives. It misses all the real cases. Yet, because the data is highly imbalanced, this completely useless model still achieves 95% accuracy. To solve this accuracy paradox, we use specialized metrics based on real-world costs. In this security camera feed, if a system triggers an extreme action for a theft, the cost of a false alarm is very high. Precision calculates the fraction of positive guesses that were actually correct, minimizing false positives. Conversely, in medical diagnosis, returning a negative result for a patient who actually has a disease can lead to death. Here, recall, or sensitivity, calculates exactly how many of the actual positive cases the model successfully found. The primary goal becomes minimizing the false negatives. Think about a spam filter. Does it need higher precision to avoid burying an important email, or higher recall to catch every piece of junk? When an application requires both, we compute the F1 score. It operates as a mathematical balance between precision and recall when both matter equally. Relying on a single accuracy number hides critical flaws. Choosing the correct evaluation metric requires looking at the specific human and financial costs of false positives versus false negatives in your exact industry. Classification models rarely output strict yes or no answers. Instead, they output a confidence percentage. To assign a final 0 or 1 output, a human engineer must set a threshold on this slider. This Cartesian graph plots the true positive rate against the false positive rate. As you shift the threshold slider, the rates change. The resulting line is the receiver operating characteristic, or ROC curve, visualizing the model's performance at every possible threshold level. In a perfect case, a specific threshold splits the classes flawlessly. The plotted line pushes straight up into the top left corner of the graph, representing 100% true positives and 0 false positives. To compress that curve into a single metric, we measure the two-dimensional space underneath it. The area under the curve, or AUC, is an aggregate performance measure across all possible thresholds. A score of 0.5 is random guessing, while 1.0 represents perfect classification. The AUC is an excellent overall grade for comparing different models. However, to actually deploy a model to the real world, you still have to pick a single operational point on that curve based on your acceptable level of risk. Real-world applications move into multi-class territory, where models must categorize thousands of different objects. The ImageNet Visual Recognition Challenge provides a clear framework for this, testing a model's ability to distinguish between a massive library of distinct categories. With multiple classes, we score models using two specific metrics. The top 1 error checks if the model's absolute highest confidence guess matches the ground truth. The top 5 error is more forgiving, checking if the true label was anywhere within the model's top 5 highest probabilities. Populating this larger matrix with raw numbers creates a problem. If your dataset contains 500 cats but only 50 cars, the absolute values make the correct and wrong predictions hard to interpret. Converting those raw counts into normalized percentages transforms the grid into an easily readable heat map. In a perfect normalized confusion matrix, the diagonal elements are a solid 100%, and everything else is 0. By analyzing the deviations off that diagonal, like noticing a cluster where the model frequently confuses dogs with cats, you see exactly where the algorithm needs modification. Ultimately, evaluation metrics function as diagnostic tools. They reveal the hidden biases, imbalanced data, and specific blind spots that headline accuracy numbers often hide.